Okay, so Happy New Year, everyone. This is Stat 100B, Introduction to Mathematical Statistics. So we originally have our classroom in Haynes, but for the first two lectures, at least for now, we will do remote lectures. And you have the Zoom link so you can be here. And the lectures will be on Mondays and Wednesdays from 12:30 to 1:45, 1 hour and 15 minutes. And our teaching assistant is Dongyuan Song here, our PhD student. So he's here to say hello to everyone, and his discussion sections will be on Thursdays. So you have two sections, so you please go to the section you sign up on my UCLA. So for our office hours, they will be on Tuesday mornings. So I will do my office hour from 9 to 10, and then Dongyuan will continue and do his office hour at 10 to 11. So if you cannot make the two office hour times, you can make appointments with us. So a brief description about the course. So Stats 100B is a follow-up of Stats 100A, which covers probability. So if you haven't taken at 100A or there's a more advanced version in the math department 170A. If you haven't taken either, so it's a prerequisite. Otherwise, you cannot really understand what we're doing in this class. So please make sure that you have the background. So you know, for example, you understand what is a random variable. So, and what we will focus on here is what we call mathematical statistics. And the key, I would say, concept is parameter inference. So basically, we will talk about our sample as IID and IID independent and identically distributed, short as IID, random variables from a distribution, which is parameterized by a parameter theta. To start with, we'll just assume theta is a scalar value parameter. So I'll give you some examples very soon. So our goal is, how do we estimate this theta from our sample? So this is the central question to be addressed in this class. And we will cover common distributions about this F, including normal distribution, Poisson distribution, exponential distribution, binomial distribution. So I would say those are the most common ones we'll cover in the class. If those don't sound familiar to you, I would suggest a review of the 100A. Okay, and also in this class, we will derive some classic distributions for statistics. By statistic, we mean it is a summary of our sample. So some classical distributions about statistics include the T distribution, the chi-square distribution, and the F distribution. So we will derive them and talk about how to use them. So there's no required textbook, but we have a recommended book by John Rice. So this is a book you can check out, and it has more contents than what we will cover in this class and more problems. Okay, so this is just a list of the contents we'll cover in this class. So probably we will not go to the regression correlation, but we'll see. In previous years, we didn't have time to go there, so we'll stop at hypothesis testing. But you will see how those concepts are connected. And also, because this is a mathematical statistics class, we will use math derivations mostly. So computer programming is not assumed, but I might use some simulation on my computer to just demonstrate the concept. I might add that to my class just to make it more intuitive, but mostly we'll just do derivation. So your homeworks here. So we will assign 7 homeworks throughout this quarter, and your homeworks will be handwritten by default, unless you want to try to use LaTeX to type up your solution. That's definitely preferable. If you want to go to, say, graduate study, then LaTeX will be a requirement, but it's not a requirement by this class. So you can feel free to do your homeworks by hand and write up your solutions. But because we have to do remote teaching in the first 2 weeks, so you will submit your electronic copy by just taking a picture of your answers or scanning your homework answers and upload the electronic copy to CCLE. So we will assign the first homework this Wednesday, and it will be due on the next Wednesday. Okay, so we might have some, because we have 7 homeworks in total, so we might just give you a break during the middle of the quarter. And also, Previously, in previous years, we had actually 2 midterms in the middle, but this year I reduced it to 1 midterm because of this remote teaching and the pandemic. So we might have to do the midterm remotely depending on the situation, but we will keep that open for now. So speaking of the midterm, the tentative date is January 26th, a Wednesday. So we will decide the time and location later, depending on, again, the pandemic situation. But if you have any time conflicts with the state, please let me know after this class as soon as possible, so we can try to find a better date if this doesn't work for many people. Okay, and the final exam will be at the time scheduled by the university. So it'll be March the 14th from 3 to 6 p.m. We may not use the whole 3-hour window. Maybe we just need two hours, but we'll see. And the locations to be determined. Okay, so basically your grades will depend on the 7 homeworks, 1 midterm, and 1 final. And also just as a reminder for the homework, for the electronic copy, if you take pictures, please combine them into 1 PDF file and upload that file. So don't just give us many pictures because that can be easily lost. Okay, and so for late homeworks and makeup exams, so we will actually I will decide whether we will allow that at my discretion, but there will be some penalty for sure. And the penalty will depend on how late you submit your homework or what the format of the makeup exam will be like. Okay, so regarding the exam later, so everyone can bring a 1-page, 2-sided letter size note if we want to do like an in-person exam. So that can capture all the basic facts you want to use. And regarding the grades, it will be curved. So I will consider both like your rank and the absolute score you obtain. So we want to be fair for everyone. So to give you a rough idea, in the previous years when I taught this class, so we have for students who got A+, A, and A-, they are about, say, around 30% of the class. So you can have a basic idea about what the curve will be like. But if, like, say we have 50% of the students who do extremely well in this class, I don't mind giving everybody the 50% A's. So that's what I mean. We will consider both the rank and also the absolute scores. Okay, and regarding the homework answers and exam grades, if you think anything is incorrect, please inform me within 3 business days of the return of the materials. By return of the materials, we mean when the graded materials are returned to you, not when you check the results. So please make sure to check them immediately. And if you find anything that's not correct, please let me know. And for this class, we will use CCLE as the only platform for everything. So please make sure that you have the CCLE login so you can check our materials. And also for your questions regarding any course contents, not administrative stuff, but just the materials, the homeworks, right? So for the contents, please post your question to CCLE and do not send us individual emails. The reason for making this policy is because we know a lot of questions may be common. So therefore, if you post your question in CCLE and we answer there, other people can see the answers. That can make our communications more efficient. And we will make sure to check the CCLE discussion forum on a daily basis. So basically, you can expect to receive answers to your questions within a day. Okay, and regarding the homework answers, I want to make sure everybody understands that the answers must be written down independently. So we encourage discussion among students, but the student must write down the answers after the discussion in an independent way. And this is very important for preparation for exams, because during exams you have to solve problems independently. And so the exam problems will be very similar to homework problems. So this makes homework problems a very good practice for preparation. And the discussion sections, so basically for the first week, I expect our TA to just cover some similar problems, just as extensions of my lectures. But in the later weeks, after your homeworks are submitted, the TA will go over the homework solution so everybody can stay on the same page. But the TA will not give homework answers before your homework is due. So this is just to make sure everybody understands. And also the office hours are not the place to ask for homework answers if the homework is not due, but we will be very happy to answer your questions regarding the contents and to give you some hints about what's the direction to go, but we will not give the direct answers. So this is just to make sure that I know in previous years, we may have some students coming to office hours just to do the homework there, but that's not encouraged. So the homework must be done independently. Okay. So another thing for the remote lecture is to keep your camera on unless you have special concerns. And also please adhere to the honor code and the code of conduct, that if you have any, you need special accommodation, please contact the Office of Students with Disabilities, OSD, or the CAE, Center for Academic Excellence, or for assisted, Center for Assisted Education. So, and academic integrity, I don't need to say that in detail, so you can read it here. So the key is to keep a current email address with MyUCLA, so you can receive our email announcements from CCLE and MyUCLA. So these are all I want to say, and there are 2 holidays, 2 Mondays in the middle of the quarter. So these are all I want to say about this class. Do we have any questions regarding the syllabus? And also, by the way, just a bit of introduction about myself. So I am an associate professor in the Department of Statistics here. So basically, I just want to clarify a little bit about the 2 types of faculty we have in the department. So like for me, we belong to the so-called tenure track, tenure line faculty, which means that half of our duties are for doing research, while the other half is for teaching. And also I didn't count the services in the middle. So basically I do my own research regarding development of new statistical methods and I focus on biomedical data analysis applications. So this class is part of my teaching duties. So I have to balance the 2 parts of the duties, but I hope that I can give you some feedback from my research experience. And also I hope to give students who want to pursue graduate studies in the future some advice. And I would say this is a very important class. It will give you the necessary preparation you need for pursuing a graduate degree in statistics or data science. And I see there's a question from the chat box. Will we also be using the new BrewLearn website? No, just CCLE. So I decided to just keep with CCLE for this quarter because I think this is a quarter we can still do CCLE. So this is like a transition period because this will be my last quarter of teaching in this academic year. So I hope to stick with CCLE to make it easier for me. So we will not use BrewLearn, just CCLE. Okay, so any other questions regarding the policies and the administration? So if not, I will just quickly go over the review materials I posted on CCLE. So everybody should be able to access that on CCLE homepage for now. So there are 3 PDFs I posted. Let me try to share the screen. So the first one is what I obtained from my colleague, Dr. Sanchez, about the 100A, Introduction to Probability. So these are some typical problems from 100A. So you can see that basically you are required to know those combinatorial numbers and also some simple integration from calculus, okay? And this, this gamma function, this is something we will also use. And this is about integration. And this is about the infinite series. And this is related to the Taylor expansion, which we'll use a lot in this class. So if those concepts are not so familiar to you, please make sure to review them to get you better prepared. And this is regarding the calculation of probability events. And this is set operation. So we will actually use those as preliminary background in this class. Okay, this is regarding the math review part. You can see this PDF on CCLE. And we also have some review materials from my colleague, Dr. Nicholas Crystal, who is also teaching this class right now, the first 2 sections. So these are some common distributions we will use in this class, okay? So maybe I'll spend some time to go over this. So basically we divide, so for random variable, what is a random variable? We often denote this by this capital X. It means a variable that can take different values. So it's not a constant, right? So like a number 1 is a constant, but a random variable may take different values at different times. So that's why we say it's random. So for example, the simplest one is I would say maybe it's not here, but the simplest one is when n is 1 here. So we call this Bernoulli distribution, which is a special type of binomial. So by Bernoulli random variable, it can take only 2 values, 0 and 1. And the probability that it takes value 1 is p. Okay, so if we have n Bernoulli variables and we take the sum of them, that is a binomial random variable. So this capital X can take value ranging integers ranging from 0 to n. Okay, and at each value, we call that small x. So small x is used to refer to a fixed value, not a random variable anymore, but a value. But since we want to be more general, we use x to represent any value from 0 to n. So for small x, then we want to ask this question. What is the probability that this random variable x, big X, picks the small x value? Then this formula gave us the probability, and we call this probability mass function, short as PMF. So this is from 100A. And with this, we can actually calculate the mean of the random variable and the variance of the random variable. So both can be done based on this probability mass function. So I will just talk about this very soon. So just this is a quick overview. And for today's lecture, we will give you a new concept called moment generating function, from which you can directly obtain the mean and the variance. So we have other discrete distributions: geometric, negative binomial, hypergeometric, and Poisson. So I won't go into details for those, but for Poisson, it's another distribution we will use. So by discrete random variable, what we mean is that this random variable big X can take discrete values. So here, 0, 1, 2, those integers are discrete. In contrast, we have continuous random variables. So here, for example, uniform variable, random variable, let's say it takes uniform distribution in a range or in an interval from A to B. So in this case, what it means is that this random variable big X can take any value from A to B. And we know that these values, so here we're talking about real values, basically. We'll forget about those not real values. Okay, so basically when we talk about the real values from A to B, we know they are very dense. Okay, so that's something we know as a mathematical fact. So therefore, you cannot really count how many values are here, but I'm not saying this in a very strict way, because we know in a more strict way, we should say real numbers are also countable, but I'm not talking about that. I'm just saying here the values are very, very dense. So for example, they say A is 0, B is 1, then we can take value 0, we can take value 0.1, we can take value 0.11 and 11111. So we can take many, many values in this window. And in this case, we say it's continuous. So the more exact definition of continuous random variable is that for a random variable big X, its probability of taking a value small x is 0 if it's continuous. But it may not be 0 if it's discrete. Okay, so for example, for the Bernoulli variable, its probability of taking value 1 is equal to P, and P can be positive. So the key difference between a discrete random variable and a continuous random variable is about whether the probability that the random variable take one single value is 0 or not. So for continuous random variable, even though it has 0 probability of picking any value, however, it may have a positive probability of being in a small interval. So here, its probability is 1 to be in the interval from A to B. So we talk about interval, but we don't talk about a single value. So that's for continuous random variable. And uniform is the simplest continuous distribution. And normal is another one that's commonly used, and exponential. So I hope everybody can review this table in detail and try to understand what we mean by here. And also, by the way, because here a continuous random variable has zero probability of picking a single value, we don't talk about probability mass function. Instead, we talk about probability density function. This is short as PDF. So for the density function, it's not really about the probability of picking a single value, but it gives you the basis of calculating the probability of the random variable in an interval. So basically, you just do the integration of this PDF in that interval, and the result will be the probability. Okay, so this is, again, a cheat sheet from 100A about the common distributions, but today I'm going to give you some more explanation about some common distributions, including binomial, Poisson, normal, exponential. So we'll see later. And next one is another PDF I posted under the review material. So right here. Also from my colleague Nicholas. So this is about the explanation of continuous random variable further, because I understand that the continuous random variable is not as intuitive and usually more difficult to understand than the discrete random variable. So here are some key concepts about it. We talk about the PDF density function. So a very important property is that the density function, if you integrate it from, we call this the value or the range where the random variable can take values from, we call it the domain. So here, let's assume that the X has a domain as the whole real line from negative infinity to positive infinity. Then the integration of the probability density function, PDF, over the whole domain must be equal to 1. This makes sense, right? This means that I have probability 1 that this random variable is in this domain. And that's just the definition of the domain. Okay, but what if we want to calculate those probabilities? What if the random variable is greater than A, less than A, or between A and B? As I said, here we will use the density function and do integration to calculate the probabilities. So we do integration from A to the positive infinity, which is the upper bound of the domain. We obtain this probability. And similarly, from the lower bound, integration to A, we get this left tail. And for the middle, A to B, we integrate from A to B. Okay, and this is an important property that for discrete random variable, if we calculate the probability of this, greater than, then the probability doesn't change if we change the inequality from greater than to greater and equal than, greater or equal than. The reason is because the probability that X equals A is 0. This is just the definition of a continuous random variable. Okay, so along with the PDF, and the PMF, probability mass function. So for both the discrete, continuous, and discrete random variable distributions, we have another concept called the cumulative distribution function, short as CDF. So for the CDF, we're not evaluating the probability or the density at the given value small x. Instead, we are looking at the probability of this random variable x taking any values less or equal than x. So we are looking at the left tail of the distribution. And that left tail is a probability, and we define it to be the CDF. So in this case, the integration goes from the lower bound, negative infinity, to the value we are evaluating, x. Small x is any value from the domain, okay? And this integration, this is the definition for the discrete, for the continuous random variable. And for the discrete random variable, I'm leaving the question here for you, and I'm going to give you an answer maybe in 2 minutes, so you can think about it. What will be the CDF for the discrete random variable? Okay. And for continuous random variable, continuing here, it's actually based on the definition of integration, okay, like this. We know from a law in our calculus, then the CDF's derivative is the PDF. So we can go from the CDF to the PDF by taking differentiation. And we can go from the PDF to the CDF by doing integration. So with the CDF definition, then we can just use the two CDFs at B and at A, take their difference, then we can immediately obtain the probability that the random variable X is in the interval between A and B. And because again, here X is continuous, we can always change the inequality sign by adding the equal sign here. So adding the equal sign here doesn't change the probability, again, because X is continuous. Okay, so these are just some very quick review about the review materials I posted under CCLE. If you have any questions about those, so again, I would suggest that a quick review of the Stats 100A will be a very good idea to start with. And also, I know that there's a very nice online course, I think offered by a professor at Harvard University. It's called, I think I can share the name here with you, just to make sure that everybody is on the same page. Sorry. So I think that class is called I think stats or probability. You can check it out on 101. So it covers a lot of the basics about probability at EDX. That's the website of Harvard. So this one covers a lot of basics, and it has a lot of, I would say, cartoons and also good illustrations to cover the basics. And it will be very important. I think they are very useful and helpful for you to understand what is random variables, because I think that's the starting point of this class. So understanding what is a random variable and why we need to use random variable as a concept, and the mathematical concept to do statistics is the starting point. So I would suggest everybody who has some questions about the review materials to check out this class, and they have some online videos, so you don't have to go through everything, but you can pick the relevant video to do the review. Okay, so now I'm going to start my class, and I will try to share the screen using the projector I have at home. So just as I said, right, we talk about random variables just as I would say representative of a quantity that can take multiple values. So just for example, let's say I consider a person's height as a random variable. So in that case, if this is a real problem, if we consider the population to be everyone in the United States, that's our population. And for the random variable height, at every individual, the height will have a realization. So for example, you may be, say, 5 feet, 7 inches, and another person may be 6 feet, right? So these are two values this height random variable can take. And then if I consider the height to take values just differ by at least 1 inch, then this height will be a discrete random variable, because can only take discrete values. So in this case, right, if it's a discrete random variable, now let me get back to the question I want to ask. So this X, okay, it's a random variable. We write this in short as RV. Okay, so in this case, whether this X can take discrete values or continuous values is the key. And let me try to adjust this a little bit, sorry, to make sure we can see it better. Okay, so if it's discrete, okay, so let me say that it's domain. Just to introduce this concept again, the domain is the value that this X can take. So let me just write this domain as this big X. So for example, the domain could be just the whole real line. And for the whole real line, I can also write as from negative infinity to positive infinity. Just one example of the domain. So any value this X can pick must be from this domain. Okay, so let's say that I pick a small x from this domain. Let's say the small x is equal to 0, for example. Then what I'm interested in talking about is this quantity, the probability that this random variable x picks the small x as its value. And just as the review we said previously, we know this probability is 0 if this X is a discrete random variable. Oh, sorry, if it's 0, sorry, my bad. It's a continuous, I said it wrong. It's a continuous random variable. Okay, this is known for sure. But for discrete, so these two things are complementary. If it's not continuous, it's discrete. If it's not discrete, it's continuous. Okay, so if it's discrete, then this value could be positive, but it still could be 0. So if it's 0, then it means that this X may be having 0 probability, but it could be actually positive. So that's special for the discrete random variable. So that's why in this case, for discrete random variable, this definition is what we call the probability mass function. PMF is defined in this way. And by saying a function, one thing we must consider is what is the argument of this function. And in this probability mass function, short as PMF, the mass function is actually the small x. The argument is the small x, which means that when we change the small x value, the corresponding probability changes, so that the output of the value of the probability mass function changes. Okay, but for continuous random variable, since this stays at 0, it doesn't make sense to call the function, right? So then what is the PDF? The PDF is not defined in this way. It's not defined in this way because it's 0 for continuous random variable, but for X is continuous, let me say it. But the PDF, okay, we have this alternative concept, probability density. Density is the keyword function. Okay, it actually gives us the basis for calculating the probability in an interval. So just as an analogy from physics, you can consider this probability density function as the, I would say, as the acceleration, while you consider the probability as the speed. So their relationship is like that. So one is the differentiation of the other. So in this case, if it's continuous, then we will say that the probability, what we had seen in the review notes before, let's say the X is between A and B, and we can write it in 3 ways by dropping the equality sign, or 4 ways actually. So these 4 probabilities are equal. Okay, so for all of them, for continuous random variable, we just do the integration from the lower bound to the upper bound of the interval using the density function. Let's say we call that fx. And again, this x is any value from the domain fx dx. Okay, and here the argument, again, the PDF function's argument is what? Is any value from the domain for which the random variable big X may pick. So one thing I realized some of my previous students got confused is about, the symbol we can use in the function argument. Actually, the function matters because it's basically a transformation. You give me an input, I give you an output, right? But the argument symbol doesn't matter. So therefore, if I write this X instead as T, let's say ft dt, it's the same thing. So it doesn't matter if I call it X or I call it T or I call it Y, it's just an argument symbol. Okay, and also another thing to keep in mind is that if it's a probability, right, we know a hard constraint is that it must be above 0 and under 1. So probability must be between 0 and 1. But for this density function, we don't have this upper bound as 1. So for the density, we only have these requirements. First, it's non-negative for any X in the domain, okay? And the second thing is that we need to have it integrate to 1 over the whole domain. Okay, over the whole domain, I call this calligraphic x dx. Okay, so for example, if this whole domain is just a real line, I just write negative infinity to positive infinity fx dx. So this must be equal to 1. So these are what we require for the density function. Okay, so given the PMF for discrete random variable and the PDF for continuous random variable, we can define this cumulative distribution function CDF. Okay, and we have the CDF for both a discrete and the continuous random variable. So it's universally defined as the probability that a random variable big X is under a single value small x. Okay, but it differs for the two types of random variables in the definition. So for this probability, if it's a discrete random variable, then we can just enumerate all the possible values under small x. Okay, so therefore, what I can do is I can write this as the probability of any value y that my big X can take from the domain under the small x, and then I take the sum of the probability that my big X is equal to y. Okay, and I can do that. That's for discrete random variable if X is discrete. And this is exactly the PMF of X at y, right? I evaluate the PMF function of my random variable at every single value y. As long as y is under small x, I sum them up. But I cannot do this for the continuous random variable because I know this is always 0. It doesn't make sense to do that. And also, this continuous x, big X, can take infinitely many values under small x. So here I do integration instead of a sum. So here what I will do is I will take the lower bound, let me assume it to be negative infinity just for simplicity, to the x, okay? And I take the PDF at y, okay? Any value y taking in this range from negative infinity to small x dy. Okay, so you see here, I can no longer use x in my integration as the symbol. The reason is that here x is fixed, right? As the value I'm going to evaluate for the probability. I fix this x, but for whatever value I change in this interval from negative infinity to x, I denote it by y. And y is just a symbol. I could also use t, I could also use r, s, it doesn't matter. Okay, so these are the CDF. And some other key concepts we will talk about are moments. Moments. They are key properties about a random variable, okay? And they are related to the distribution of the random variable. So what is a moment? To talk about moment, we talk about the first moment to start with. First moment has a more common name as the mean, okay? And also the expectation. It's defined as the expectation of a random variable x. So please note that in this class, we will stick with using capitalized symbol for a random variable. And we will use the big X for random variable x and small x for a particular value. So we'll just do the distinction consistently. And here in the expectation, I think you have seen it from 108. So here the brackets are often ignored just for simplicity. So you will see people sometimes write it just as EX, just as a simplicity notation. So how do we define this? The definition of this will actually depend on integration or summation. Again, depending on whether x is random, it's discrete or continuous. So specifically, what we will do is define it as, if it's discrete, let me just write it, or maybe I just write it down here. If it's discrete, then what I'm doing is I take all the possible values my random variable may take in the domain, okay? Small x in this set. And so for every possible value it takes, I multiply the value by the probability that the random variable takes this value. So you can imagine if all the probabilities are equal, that means we are under the uniform distribution, then the expectation is just the average of all possible values. But if the values are not taken at equal probabilities, we need to weigh each value by the corresponding probability. And that's the intuition behind this expectation for me. So if it's discrete, we do this. But if x is continuous, okay, then doing this doesn't make sense because every probability is 0. It doesn't make sense anymore. So what we do is that we change the summation to an integration. So we integrate over the whole domain. And for every value x may take, we multiply by the density, the corresponding density. So density will replace this probability mass, dx. Okay, so that's the first moment, and this is the definition of expectation. So depending on what we are taking expectation over, so basically this is the quantity we're taking expectation over, we will change here correspondingly. So for example, if I'm looking at the second moment, okay, which is defined as expectation of x squared. So the first, second, these all refer to the power of x before we take expectation. So then correspondingly, you know, for the discrete and continuous formula, the domain remains the same domain. But here, we'll change this x correspondingly to x squared to x squared. In the discrete case, we still weight each x squared by the probability. In the continuous case, we multiply it by the density. So then you can see for the third moment, we'll just change to x cubic correspondingly fourth moment, x to the fourth. So these are what we call the moments. And as you can see, these moments are properties about a random variable, right? And the random variable is specified by its distribution. So usually, you know, we talk about random variable and its distribution exchangeably. Like when we say a normal random variable, we mean the random variable follows a normal distribution. So a random variable is specified by its distribution. And intuitively, what is this distribution about? It tells us how likely this random variable may pick each value. So with that, we totally understand the behavior of this random variable. Okay, so far, do we have any questions about those concepts? So we're just talking about probability. We are not talking about statistics yet. So this class, for now, for today, we'll talk about the moment generating function next, and that's about how do we generate those moments. And it is still a probability concept. Okay, so any questions so far before we start talking about the moment generating function? All right, so if there are no more questions, I will move on to talk about the moment generating function. And also, by the way, so after today's lecture, I will just scan my notes, the handwritten notes, I'll post them to the CSW for your information. So if you didn't capture something, you can take a look later. Okay, so now moment generating functions. It's a probability concept invented by mathematicians. in early days. So short as MGF. It's just a nice mathematical way to summarize the moments, basically. So specifically, how do we define it? Oh, and also, by the way, there's one thing I forgot to mention, but I think it's worth mentioning regarding any probability. Okay, so regarding this probability, not necessarily the CDF, but any probability like here, we can actually write it as equivalently as an expectation. So we can write it as the expectation of an indicator function that x is between A and B. Okay, so I think I'm going a little advanced here, but I hope some of you can understand. So here, when we take expectation, the key thing to check is what is the random variable. And when I write it this way, here the random variable is the indicator. This indicator itself is a binary random variable. So I can say this indicator itself follows Bernoulli distribution, takes value 0 or 1. And what's its probability of taking value 1? That probability is exactly the probability that x is between A and B. So you can see why. Because this indicator is equal to 1 if and only if when x falls between A and B. So therefore, its probability of taking value 1 is exactly the probability x is between A and B. And also because we know for Bernoulli random variable, its expectation is equal to this probability. That's why we have these two things equal. So therefore, we can often equivalently write the probability as the expectation of some indicator random variable correspondingly. And this can make some of our discussion easier. But I'm just making this as a side note. So it's okay that if this is a little bit advanced for now. But yeah, I think it's just interesting to know this. Okay, so moving back to the moment generating function, its definition is actually about, let me make it a little more specific. So for this class, because we are intro class, right? So we don't want to make it overly complicated. Let's just assume that here our random variable x is real valued, okay? Takes real values. Okay, then when we define the moment generating function, we think about another real value t. So for any real value t, we can define the MGF of x. So just as the PDF, PMF, CDF, this MGF is also a property about a random variable, a function about some property about the random variable. We define it as using this notation mx. So we put x random variable in the subscript to be sure that we're talking about x MGF, not something else MGF, okay? So mx is the MGF function. We evaluate this function at this real value t. So in other words, the argument of the MGF is a real number, real value. Once we input any real value t, we will evaluate it, right? And how do we define it? We define it as the expectation of the exponential function raised to an exponential function at t times big X. Okay, and again, when we look at expectation, the first question to ask is, what's the random variable? Here, the random variable is e to the tx. And let me ask you, in this random variable itself takes what values as an exponential function? Positive real values, right? Exponential function cannot be negative. But here, why is a random variable? Where is the randomness? The randomness comes from big X. That's the random variable here. Since this big X can take different values, then correspondingly, exponential tx takes different values. So that's why exponential tx is a random variable. but t itself is not random. We fix it at this t, okay? So why does this definition make sense? We'll see very soon. And we add the name moment generating function. So we will know that it can give us moments. It can generate moments for us. Okay, so first of all, look at this definition, expectation. Based on what I just said about the expectation for a discrete random variable and the expectation for a continuous random variable, we will have two versions to define it, depending on x being discrete or continuous, right? Because intuitively, you can know when x is discrete, then e to the tx is discrete. When x is continuous, then e to the tx is continuous. Okay, so when x is discrete, again, we take the summation. Okay, for all possible values, this x can take small x, and I do exponential to the t small x. Now I'm basically realizing this random variable at a value small x times the corresponding probability. Okay, so this is the formula. If x is discrete and if x is continuous, we will do the integration. Okay, so this one I can just write negative infinity to positive infinity, since it's the real line, exponential tx times the density function fx dx if x is continuous. Okay, and I forgot to say that here, if it's continuous, we just assume the PDF to be f. So we'll use this notation consistently. So you know, when we write small fx, it means the density function. Okay, so now why can we generate the moments? So to understand this, we will use a very special property about Taylor expansion of the exponential function. So think about this exponential function here. If we do Taylor expansion on it, okay, e to the tx, I'm just taking the random variable still with me, but do Taylor expansion on the exponential function. So actually a fact is that its expansion looks like 1 plus 1 factorial tx times tx plus tx squared divided by 2 factorial plus tx cubed divided by 3 factorial, and so on. This is the special form of the Taylor expansion of exponential function. And this actually converts, this expansion converts an exponential function to a polynomial function. And you know, this polynomial function will remind us the moments, right? If I now add expectation to the left and right-hand side, adding the expectation to the left-hand side will give me the definition of the MGF. And to the right-hand side, I would just have 1 plus, you see, and this is a property, that is, we can make the expectation enter each term in the sum, and we can get t out because t is not random, so we only keep the random terms in the expectation, okay, and so on, plus t squared expectation of x squared plus t cubed times expectation of x cubed, and so on. So you see, I'm having the moments. Okay, so the first moment is here, second moment is here, third moment is here. This is by doing Taylor expansion on the exponential function. And what if I do Taylor expansion on the MGF directly? I'm going to use the definition of Taylor expansion. Expansion on mxt. Okay, if I do this, So now please make sure here the argument is t only. I'm going to do this Taylor expansion on this function of t. So you can see that by the definition of Taylor expansion, if I expand it around 0, okay, I have mx0 here plus, again, 1 factorial times t times mx first derivative at 0. That's the first term in the expansion, plus 2 factorial denominator t squared times mx double the second derivative at 0, plus 3 factorial t cubed times the third derivative at 0, and so on. And also here for the above line, you know, this is our definition of mxt. So basically these two things should be equal and we should be able to match their terms. So first of all, let's look at what is the moment generating function when t is 0. So by definition, when t is 0, it's exponential 0, that's 1. So we know this term is 1. So therefore, you see, we can exactly match the terms in those two expansions. One on exponential before taking expectation, one on moment generating function directly. By matching the terms, you see 1 is 1. And here we have a term for t. Here we have a term for t squared. Here we have a term for t cubed. So therefore, the coefficients for t, t squared, t cubed should match, right? So you can see by matching those two terms, that those two equations, I call this 1, I call this 2, because 1 should be equal to 2. This will give us very interesting relationships. That is, my expectation of x, the coefficient of t, should be equal to the first derivative of the moment generating function at 0. And the expectation for x squared, the second moment, should be equal to the second derivative of the MGF at 0. And the expectation for the x cubed, third moment, should be the third derivative of moment generating function at 0, and so on. So we can go to other moments. So, and this works as long as the Taylor expansion works for the moment generating function. So in other words, we need this moment generating function to be continuous or smooth enough around 0. Okay, so we can have its first derivative, second derivative, and so on to do this Taylor expansion. So it must be a very smooth function around 0. So this can be done. And once it's possible, then we can use this moment generating function, taking its derivative at 0, and we will obtain the corresponding orders moment. Okay, does that make sense? So in other words, in summary, this means that we have expectation of x to the power k equal to the moment generating function taking the kth derivative at 0. Okay, and this k can be 1, 2, and so on. But the question, the condition is that if we have m, x, k, this function, let's say t, exists at an interval around 0. So this is about the mathematics regarding the Taylor expansion when it holds. Okay, so any question about the definition of moment generating function? You can think about it as a very concise way of summarizing all the moments about the random variable. Once we have the MGF, as long as it's smooth enough around 0, we can obtain the moments of the random variable in a very straightforward way just by taking the derivatives. And also, the moment generating function has another very important property, for use. So that is for some common distributions like normal distribution, exponential distribution, which we'll see later, we can have its moment generating function. And you can actually find this on Wikipedia for those common distributions. And so therefore, if you have some, you perform some operations on your random variables, say like taking their sum, and we will see that the MGF has some nice properties for sum of random variables. And if the sum has an MGF of your familiar form, then you can say, oh, the sum is also that random variable, is also following that common distribution. So in other words, you can go from the MGF using its nice properties and then compute it and then use the result to tell you what distribution this random variable follows. So that can be a nice application, which we'll see very soon. But first, let's try to derive some MGF for some common distributions first. Okay, so let's start with the binomial distribution. Let's say X follows binomial N P. So N is the total, P is the success probability that it has a successful draw. So you can consider this as if I toss the coin for N times and the probability of getting a head is P for each time, then how many heads do I get after N tosses? And that's capital X. So in this case, we will have the M. So basically, let's try to look at the PMF first. Okay, for X taking value small x, the PMF we know is equal to, there are how many ways of me getting X heads, right? Out of N, I can choose X to be head. And for each head, the probability is P. I multiply them, so I get P to the power X. And I have N minus X tails. Each probability is 1 minus P. And I multiply the probabilities together. So I get the power N minus X. This is the PMF, probability mass function. And here, X can go from 0, 1, 2, N. These are the possible values you can take. So using this, now let's do the definition of MGF. So MX at T, by definition, it's just the expectation of exponential TX, right? Now X is discrete. We do the summation. The small x can go from 0 to n integers, and we have exponential T small x, probability x equals small x, right? And now I'm going to use this formula from above. So I have exponential Tx times P to the power X times 1 minus P to the power N minus X. This is the definition of MGF. So what's left for me is to simplify this sum. How do I simplify it? The obvious way is to combine the terms. Oh, sorry, I missed the N choose X. I should put it back here. Okay. So it's to combine the terms. Now here the X, Tx is here, P to the power X is here. So if I multiply those two, you know, a natural result is that I can have, just go one more line, X from 0 to N. I put N choose X to the front, this number. And I combine the two terms with X in the power. So I have E to the T times P, their product to the power X, times 1 minus P to the power N minus X. Okay, so now I'm at the so-called binomial formula, right? So I'm having this, so it's basically when I have two things add up and I raise the sum to the power X, I'm talking about this. If I have A plus B to the power N, how do I calculate this? This is called a binomial formula. So I can just assign N by dividing it into two integers, say 0 and N, 1 and N minus 1, 2 and N minus 2. And I just assign the power, decompose n into two integers and assign the two integers as two powers to a and b. And also I will consider that how many ways are me to assign, say, 3 to a, n minus 3 to b. And there are n choose 3 ways to do that assignment. So basically, this is a very interesting result. That is, I can write this as x from 0 to n. X is the power I assign to a. So I have n choose x, and a to the power x, b to the power n minus x. So this is what I mean by a binomial formula. And you can see the similarity between here and here. Here we are also dividing n into, not dividing, we are decomposing n into x and n minus x, two integers. And then we assign these two as two powers to two terms. So clearly you see, based on this fact, because of this fact, we can write this sum as just ET times P. Try to find another pen. So ET times P plus 1 minus P. This is my term A. This is my term B to the power n. Okay, so you see T, here the argument of my moment generating function, it can be any real number. It will actually be in the term on the right hand side as e to the t. Okay, so this is the MGF. Now let's quickly verify if this MGF can give us the correct moment. So based on our knowledge, we know that in this case, for the binomial x, expectation of first moment is actually n times p. Okay, another result we know is the variance. The variance of x is n times p times 1 minus p. So regarding the second moment, expectation of x squared, a very well-known fact, and it's very easy to use, is that it's equal to the square of the first moment plus the variance. So please note that the second moment is not equal to the variance. Their difference is the square of the first moment. So basically the second moment is greater or equal than the variance because of this term. So therefore, if we do the algebra, it's actually n squared p squared plus np times 1 minus p. Okay, so this is what we know. Now let's try to verify these results using verify EX first moment and second moments by using the MGF we just obtained. Okay, so let's do the first derivative of the MGF at t. Based on this result, we have t inside, and also here the derivative is against t. Okay, so then t is inside, so we will use the chain rule from calculus. So first take the derivative of the whole thing. So it will give me n times ETP plus 1 minus p to the power n minus 1. And then I will go to the inside and take the derivative here. So you know the derivative of ET stays as ET and it's multiplied by p, so p stays. But 1 minus p will go away because they don't involve t. So times ETP. Now let's evaluate this as 0. So this will tell me, you know, if I evaluate this first derivative as 0, you know, this becomes 1. ET becomes e to the t becomes 1. So p plus 1 minus p is 1. So I get 1 here, but n will stay, okay? And here is 1, so I have p. So, you know, it's the same moment, same first moment as agreeing with my knowledge. Now let's do the second moment. For the second moment, I'm going to take derivative against t again, but here I have two terms involving t. One is here, the power term, one is here. So I need to take them separately, okay? So first of all, let's take the derivative for t in the first term and keep the second term as is, plus let's keep the first term as is, taking the derivative for the second term. So let's get the result. For the first term, I'm going to use the chain rule again. N times n minus 1 ETP plus 1 minus p to the power n minus 2 times ETP. That comes from the chain rule, but don't forget the second term. So it stays here, ETP. Okay, and now I'm taking the derivative for the second term and keeping the first term as it, n times ETP plus 1 minus p to the power n minus 1, unchanged. And here, ETP derivative against t stays as ETP. Okay, so for now, these two terms, now I evaluate the second derivative as 0. So you see, when t is 0, again, I'm having this term as 1. Okay, 1. Okay, that's what I have, p and p, so I have p squared. And for the second term, I have n, 1, 1, and p. So now if I see, if I span the terms, it's actually n squared p squared minus n p squared plus np. And if I have the second moment above here, I expand it, it's the same, n squared p squared plus np minus np squared. So you see, they are exactly the same. So basically, I'm just showing that using the moment generating function we derived, we can recapture the moment, which suggests that we are doing it correctly. So as a sanity check. Okay, that's the first example, binomial. The second example, we'll look at another discrete random variable, Poisson. Poisson lambda. Okay, as a Poisson random variable, the values x can take is also 0, 1, 2, up to, now it's not upper bounded by n, but up to infinity. Okay, so here, let's start with the probability mass function as well. It's defined as this one. So lambda to the power x times exponential to the negative lambda divided by x factorial. And here, x can take value from 1, 0, 1, 2, up to infinity. So again, you see, one important result we will make use of the PMF, probability mass function, is that if I take the sum over all possible values of my random variable, let's say I let x range from 0 to positive infinity in integers, and I take the probability mass function. So their sum over all possible values should be equal to 1. Okay, and this is a fact we are going to use to obtain our MGF. So in other words, you see, what this suggests is that if I take the sum of this special form, lambda to the power x, e to the negative lambda, x factorial, is equal to 1, as long as lambda is positive. So this is required to be, for the Poisson to be valid. So that's why we need to bear this in mind. And also for the Poisson distribution, we know that it has a special property, that is its first moment expectation is equal to lambda, and also its variance is equal to lambda. So we are going to verify this using this knowledge. But just for now, let me just open this up a little bit and let you finish, and we can come back to this next time. So here it's a discrete random variable. So the moment generating function is defined as expectation as a sum, right? E to the t small x, probability that x takes this small x. Okay, so I'll stop here and you're going to use this formula, put it inside, and then try to simplify the summation using this fact. So the hint is that you will try to come up with some new lambda here and here so that you can, when you take the sum over x, then you can still use this result that the sum is 1, but you will have some remaining terms here because when you try to make this form, you are going to have some remaining terms, and those will be whatever left for you as the MGF. So I will stop here and try to solve this as the exercise, and we'll come back to give the answer on this next time. Okay, so I think that's all for today. If you have any questions, you can post them to Cecily. And see you on Wednesday.
Thank you.
Thank you. Oh, we have some questions on chat box, sorry. Let me see. Okay, so I'll just answer here. I got a question about what are the applications of moments? Very good question. So I will say using the first moment roughly is the location, the mean, right? And the second moment, you have seen that it's related to the variance. It's regarding the spread. And for the third moment, it's regarding this, we call the skewness, like how tilted your distribution towards the left or the right. And for the fourth moment, it's kurtosis. It's regarding how heavy tailed the distribution is. So basically the moments are just some mathematical summaries of a distribution, and using the moments you can have a better understanding about the distribution. But for most applications, I would say people are only concerned about the first and the second moment. But for financial data, usually people believe it's very heavy tail, which means that they are not like a normal distribution that can just be captured by the first two moments. Because for a normal distribution, the mean and the variance, the two things alone can fully specify it. Right? You don't need to go to the higher moments, but in some other more special distributions, the moment you may want to go to higher moments. So yeah, so I would say moments are just a very nice way for summarizing a distribution. Okay, my pleasure, and see you on Wednesday. Bye.